Welcome back to the deep dive. So you've sent us this incredible stack of source material, and it's all focused on one thing: the nuts and bolts of C++ SAT, specifically those foundational libraries.
That's right. And our goal today is pretty simple, actually. We're giving you a shortcut, a way to decode the C++ standard library, the STL, and see it as, a comprehensive tool chest.
Oh, tool chest, I like it.
Yeah, it's a huge set of pre-written code. It's designed to handle all those generic common tasks you run into, things like basic input-output, math, data conversions, and even just getting your output to look sharp.
Okay, so let's unpack this ecosystem, because it's not just the standard library we're talking about, is it?
Not at all. The power of C++ really comes from this wider landscape of tools. The standard library is the bedrock, sure. It's what every compiler ships with.
The guaranteed stuff.
Exactly. But C++ is old enough that it also fully supports many of the older C libraries. And this is the critical part. Once you master the standard tools, you open the door to the real industrial strength libraries.
Okay, give us the hook right now then. What are those industry titans people move to after they've got the basics down?
Well, the sources call out two essential ones. First, there's Boost. It's practically a library of libraries. It's used everywhere in heavy-duty applications because it tackles complex stuff.
That what?
OS interactions, threading, advanced data structures, things the standard library might not fully cover yet. If you see complex cross-platform code, you're probably looking at Boost.
And the other big one.
Google Test. This is the absolute gold standard for unit testing. You hear people talk about writing reliable code, right?
All the time.
Well, Google Test is what helps you prove your code is reliable. And understanding the standard tool chest we're diving into today it's the foundation you need before you can build with powerful tools like Boost and Google Test.
Fantastic. Okay, so here's the plan. We're starting at the very beginning, how we talk to the program with input-output. Then we'll get into managing data strings, conversions. After that, we hit the math functions. And finally, the fine art of making your output look polished. Let's start with the basics of inclusion.
Right. To use any of this code, you first have to tell the compiler where to find it. This is called the mechanism of inclusion, and you can't skip it. You use a specific syntax, the hashtag include at the top of your file.
And once that line is there,
you instantly get access to every identifier defined inside, all the functions, the operators, the data types, everything.
And you mentioned C++ uses older C libraries? There's a visual cue for that in the include syntax, right? A way for us to spot when we're using those legacy systems.
That's a great point, yeah. When you include a C library in C++, say, it usually gets a C prefix. So instead of the C++ ioStream, you might see cstdio, or cmath for math, cstdlib for general utilities. That little C is your flag. It tells you you're dipping into the classic C world.
Okay, and since we're at the foundation, we have to talk about the first library pretty much everyone uses, ioStream.
It's our anchor, for sure. ioStream defines the core tools for standard input and output. Identifiers like syn for reading from the keyboard and count for writing to the screen. And, of course, endl.
Wait, let's pause on endl. Everyone knows it makes a new line, but there's a second thing it does, something about flushing the buffer. Why does that matter?
That's a really crucial insight. So when your program writes output, it usually doesn't send every single character to the screen one by one. It's inefficient.
Right.
It collects them in a temporary holding area called a buffer. When you use endl, you're forcing the program to flush that buffer. It immediately pushes everything it has stored out to the screen.
And why would I need to force that?
Well, maybe you're debugging and you need to see output right away. Or if your program is running on a server, you need to guarantee the message was sent, not just sitting in a buffer somewhere. If you just need a new line, you could use the end character. endl gives you that extra certainty.
Perfect. Okay, so now we can talk to the program. Let's move into section 2, because data in the real world is messy. We have to handle text. We have to convert things constantly.
Oh, absolutely. Data conversion and string handling are, they're central to almost any real application. Let's start with the C++ string library. This gives us the modern string data type, which is just far more flexible and robust than the old way.
And we've probably used one of its key features already without even thinking about it.
I'm sure you have. If you've ever tried to print a number along with some text, you need to convert that number first. That's toString. That function comes from the string library, and it's vital for turning numeric data into text so you can display it.
Now, this is where the sources get really insistent. We need to hammer home the difference between the modern C++ string and the old C-style string.
This is probably the most important takeaway of this section. It really comes down to safety. The modern string library is fundamentally different from the old C library, C string.
How so?
C string works with C-style strings. And what are those? They're just arrays of characters. The key difference is memory management.
Which means?
What for us?
It means the C++ string type handles all the tricky memory allocation and resizing for you automatically. The old C-style strings make you do it all manually, and that manual control is where bugs, buffer overflows, and a lot of security flaws come from. The modern way is just safer and simpler.
So when we see that std prefix before string,
That's your signal. Using the std namespace, that std tells the compiler you want the modern safe tool, not the legacy one.
that makes so much sense. Okay, let's pivot to general data conversion. For that, we're often looking at the cstdlib library.
Right. Think of cstdlib as your utility belt. It's a C library, but it gives us these super useful typecasting functions. Even simple ones we use all the time, like float, int, double.
But the really interesting part is when you get data as text, like from a file, and you need to turn it back into a number. Exactly. For that, cannylib has targeted functions. So, atof converts a string to a floating point value. For integers, you have atoy, atol, and atol, which convert to standard long or long integers.
And when we use these functions, we're passing a value inside the parenthesis. Before we jump to the math section, let's define that piece of vocabulary for good.
Yes. That value is called the argument. It's the specific data or variable that you're feeding into the function so it knows what to work on. It's a critical term, especially when we start doing calculations.
Which brings us right to section 3, mathematical muscle. If you're solving any kind of real problem, you're going to need more than just plus and minus. This is where cmath comes in.
Right. Canalin is your direct pipeline to all the common mathematical functions. Think back to algebra and trigonometry from high school. All of that lives in here.
And that concept of the argument we just defined becomes critical here because math often involves nested expressions.
Absolutely. If you see a math expression like, say, log of 1 plus x, you have to calculate the 1 plus x part first. That's the argument. In C++A, it's the same. The expression inside the parenthesis is evaluated, and then the log function is applied to that final result. Understanding that order of operations is key.
So let's say I'm tackling a problem from the sources, like calculating the distance between 2 points. What tools does schemath give me right out of the box?
It gives you everything you'd expect. Abs for absolute value, squirt for square root, which is essential for distance calculations, or for that Heron's formula mentioned in your material. You get sin, coses, all the trig functions, plus pow for exponents, and log for logarithms.
Yeah.
It saves you so much work.
That covers the big math problems. But sometimes we just need to do a quick check, like, is this character a letter? For that, we can turn to scactype.
Yeah, ctype is a neat little C library for character work. It has simple utilities like tolower x, which gives you the lowercase version of a character, or toper x for the uppercase. And really useful checks like isalpha x, which just tells you true or false. Is this character a letter? It makes data validation a lot cleaner.
Okay, so we have I/O, we can handle data, we can do complex math, but messy output can make even the best code look, well, amateurish. This brings us to section 4. The art of formatting. We need polished output.
This is where iomanip comes in. It stands for IO manipulators. This library gives you really fine-grained control over how your data looks when you print it.
And the key tools here are these parameterized manipulators. The ones that need an argument, that's why you need the library. So what are the essential ones?
Okay, there are 3 you'll use constantly. First, set precision. That controls how many digits you see after the decimal point. Then there's set sopper, which sets the minimum width for the very next thing you print.
The next thing, that's an important detail.
A very important detail. And finally, set fill, char. That lets you choose the character to fill in the empty space that set might create.
Let's make this practical. Your sources mention creating a clean, tabular report student name, age, GPA. How do we use these manipulators together to make that look good?
This is where it all clicks. You've got a name, which should probably be left justified, but the age and GPA, those are numbers. They should be right aligned so the decimal points line up nicely in a column.
So if I use set 20 for the name, how do I make sure the numbers line up in their own, say, 5-character column?
You combine them. By default, output is right aligned. So for the name, you'd use std.left, which you get from iostream, followed by set20. But for the numbers, you'd switch back to std.right, or just let it default, and then use set.do5.
And what if I wanted leading zeros for something like an invoice number to fill it out to a certain width?
That's a perfect use for set fill. You set the fill character to a 0, then you use set to or whatever width you need. The stream will automatically pad the number with zeros until it hits that width. It's how you get that uniform professional look.
Now, sometimes we need to treat a string itself as a stream for complex parsing. That's where stream comes in. Why would we need to do that?
Because a single string often contains multiple pieces of data. Think of reading a line from a file. Stream lets you treat that string like it was a file or the console. There are two main types.
Break it down for us.
First, base a string stream. The I is for input. This is fantastic for parsing. Say you read a line of text, John Doe 21 3.8. You can put that whole string into an iString stream. Then you can just use the normal extraction operator, hex, to pull out the name, then the integer, then the float.
So it picks the data apart piece by piece into the right types. What's the opposite?
That would be basic string stream. O for output. This is great for building complex strings. Instead of endless plus signs to concatenate things, you just stream different data types, integers, floats, text into the offstring stream. When you're done, you pull out one single, perfectly formatted string. It's so much cleaner.
Okay, before we wrap up, we should give a quick nod to the C alternative, cstdio, and specifically the printf function.
Yeah, printf is a workhorse. A lot of programmers still reach for it for quick formatting. Instead of chaining a bunch of manipulators, print uses these special format specifiers like % for an integer or %2f for a float with 2 decimal places. It can be a really fast way to get precise output without all the setup.
This has been a true deep dive. We've gone from I/O and math to string safety and formatting. What's the big picture here? The main takeaway.
The big picture is interconnection. You see now how solving a real problem means weaving these libraries together. You need cmath for the math, iomanip for the report, and stream to parse the input. Mastering these core tools is what lets you move from just learning syntax to, building complex real-world algorithms that actually work.
So if you understand these core libraries, you're immediately faster, safer, and just more capable in C++10. And this applies directly to the source problems you're working on.
Precisely. That is the entire point.
And as always, we want to leave you with a final, provocative thought based on the challenges in your source material. We know you're working on problems using things like Heron's formula for a triangle's area. So let's connect the dots we drew today. If you're implementing a formula like Heron's, which single mathematical function that we talked about today is the most crucial for getting it right? And why does a rigorous understanding of the argument ensure you use that function correctly every single time?
Think about that connection. The formula, the complex expression you have to build for it, and the one function that gives you the final answer. That relationship is the key to accurate programming.
Until next time, keep exploring the source code.